All right. So, hey, Professor Schaub, can you tell us more about who you are?
Sure. I'm a full professor at the University of Colorado in Boulder. Specifically, I work in the SMED Aerospace Engineering Sciences Department here.
Mm-hmm. Yeah. So why did you want to become an aerospace engineer?
Well, that goes way back to childhood. I grew up in Switzerland, and back then in the 70s and 80s, there definitely wasn't any really aerospace programs in Switzerland. Certainly no companies, nothing like you have here. There was companies in Germany and France and Italy, England, who have aerospace stuff. So I spent a year as a high school exchange student living with an American family. And my American host sister at the time went to Texas A&M. And so I got to read through her undergraduate handbook and just try to figure out what's this college stuff, where do I want to go? And I saw all these degrees. And I always had a passion for space and I had a passion for math and software and all this stuff. And I really hadn't heard of aerospace engineering. I'd heard of aeronautical. We have aeronautical in Switzerland at the time, but not the aerospace part. So to me, that was really cool because it combined the things I loved. I didn't want to necessarily do pure physics or pure math, but really, how to put this all together and move humans more into space. So that was kind of what got me going. And then as a result, I ended up, after my Swiss education all finished and I did all my stuff there, I came to the US to pursue an aerospace degree. Yeah.
Mm-hmm. So your work is directed a lot towards space and space exploration. Can you elaborate more on what you want to accomplish?
Yeah, so every professor here has their own research lab. This is a research university, so I have currently about 14 doctoral students working with me. There's about 10 master students, a research associate. She's helping me with some advanced software, several undergraduate research, so you're looking at a group of 20 people. As a professor, one of the big goals for me then is helping the young researchers become full-grown, so to speak, researchers. I have my goals and visions, but so do these, PhD students, graduate students as well. So it's always a combination. But the overarching thing, you can see the logo behind me, AVS stands for Autonomous Vehicle Systems. We haven't really worked with manned or human in space flight kind of systems. It's all been typically autonomous, but we're dealing with how to advance autonomy. So if you're looking at satellites, how do they rotate? How do they point at the stars? How do you get them to Mars? That's one of the things we worked on a mission with United Arab Emirates. So our stuff is flying around Mars now and students got to work on that. How do we do exploration? How do we move in space? Space debris is a huge topic in my lab. That's one of the topic areas of interest. How do we move debris? How do we do servicing and docking, close proximity operations? It's so easy on the Earth. The car needs service. You drive up somewhere, some human comes up, changes a tire, fixes something, goes. In space, it's, just getting close is really, really hard. And that's where we're going right now. I think it's becoming more Earth-like, but it's going to take us still a few more decades. So that's kind of my lab, the autonomous part, really, to get how to move, how to control, how to maneuver within Earth system, Earth, Moon, and now also solar system. Yeah.
So how do you think on your work in space aircraft is going to change the design or improve the design of the future aircraft, future spacecraft?
Yeah. One of the particular areas that's getting a lot of interest from my research lab, the AVS lab, is really using machine learning as one. You may have heard of SpaceX trying to launch satellite constellations that have not just tens, but hundreds, if not thousands of satellites, right? And you cannot control these satellites like you did back with the Apollo missions or the space shuttle missions, where it was the one thing and you got 40 engineers watching every little signal day and night. So other companies like Planet Lab already do this. They're flying lots of satellites and they treat them just as a node in a computer science network, not necessarily as an aerospace thing. And it's changing how we operate. So the things we're doing in my lab deal a lot with autonomy to make things more efficient, to make it more scalable. So that's around the Earth. That brings costs down. I think that's a hugely important thing. Access to space is coming down, but operating satellites, the humans become the expensive part. If you need 20 engineers all the time watching all of this. This is very expensive. But also with autonomy, the big thing that comes out of the lab is, if you're going around Jupiter, all those moons they want to explore, they want to go to Europa now, look at those ice fields and do samples and asteroid return missions and so forth. The more we can put out autonomous systems that can independently go map, figure out what's happening. Like just as an example, Enceladus is one of those moons that has these volcanic ice eruptions that happen, but it's impossible to predict when they're happening. So you don't want the satellite to go, yeah, I'm talking, I'm going to ignore this cool stuff happening. I'm going to talk to Earth right now. It's like, yeah, you can wait talking to Earth for 10 minutes, turn around, take a picture, and then come back, right? So it's this kind of, and JPL, others are doing that, this kind of a smarts and intelligence, how to bake what we do as humans so easily into a spacecraft and fly that. I think that's, so I would say that's kind of, like with your car, autopilot modes these days, auto driving cars, we're further behind in space. It's a very different environment, but that's kind of what we'd like to do, that we can let the spacecraft be more on autopilot. I think that's what we're working on in my lab.
And you also do research on debris mitigation, how in particular ways are you trying to mitigate debris, and in what situations are you trying to mitigate debris?
Well, there's been a series of students doing work in this area with space debris. There's two classic regions around the Earth. One is called low Earth orbit. Those are a few hundred kilometers up. And then there's the geosynchronous orbit, which is about at a radius of 42,000 kilometers. That's where your communication satellites are, because the orbit period is 24 hours. So as the Earth rotates, the satellite just keeps the same position over the Earth. That's why your direct TV antenna doesn't have to scan the sky to follow the satellite. It's always over the same point of the sky, right? So it's a really valuable space. And we've done a lot of work in the geosynchronous region. That's where all the weather satellites are, the communication satellites and Earth observing satellites. And but it's a very narrow region. And they've been flying it for decades, and then things are flying around, but there's about 400 active satellites, well over 1,000 school bus size, big defunct satellites, end of life. Some of them may have broken at some point, and they're just flying around there. And we're starting to study how much of an impact this is going to have, and how do you grab a tumbling school bus in space and move it out of the way. So one of the things in my lab that we're looking at is the electrostatic tractor. So like Star Trek, Star Wars tractor beams, we're using an electron gun to create electrostatic forces between two objects. And so by charging up the other object with a negative charge, I make myself positive, I create an attractive force, and then you can modulate these fields, and you're flying in a space plasma, so it gets complicated. But still, that's kind of the idea, that without touching it, we're actually looking at how can we pull it, or if it's tumbling, how can we modulate the fields to slow it down? And then you can physically go grab it, fix it, service it, move it, that kind of stuff. So that's the big thing we're working on in my lab, primarily. Yep.
So what has been one of your toughest or most challenging accomplishments so far?
Definitely this Mars mission. There's at this University of Colorado, there's a huge research center called LASP, Laboratory for Atmospheric and Space Physics. It's kind of like JPL belongs to Caltech. JPL is kind of the big space center. We have something called LASP. It's older than NASA even. It's been around for a long time. And they were very fortunate they got selected to work with the United Arab Emirates to jointly make this Mars mission going. And my lab specifically worked very closely with LASP. So it's not just theory. We're working very closely with the United Arab Emirates and LASP on the engineers, the scientists, to develop the full attitude guidance system. And it's working brilliantly. That's always nice to see. But the last 4.5 years have been a lot of work to get to this point.
Yeah. So what is a milestone that you're looking forward to, like a major milestone?
Well, that just was a major milestone, I would say. You're looking at somebody here in the mid to late 50s already. So I think I've accomplished a lot actually in my career. You start to think forward where you want to go next. I've been a professor for many, many years, but I think I'll continue to work in aerospace, but professors don't necessarily always stay professors. I might also do small business. I think it's super exciting these days for young, space enthusiasts like yourself to get into this field, because it's space is everywhere, There's tourism coming up pretty soon. There's all these different rockets that are being launched. These commercial systems are happening. They want to do space mining in the future and get all these other good, cool things going. There's a lot of cool projects, and I think I wouldn't mind being part of that too. And that might be through university or just as a consultant outside. We'll see.
So what do you predict is going to happen in the future with your research?
It's really hard to predict research, right? If I knew exactly what's going to happen, it's not research, it's production. The research is always, as I teach my students, the research is really the exploration of the unknown. We have ideas, concepts. How do we get to Mars? How do we get to land on an icy moon around Jupiter? How do we navigate autonomously using cameras? All this kind of stuff. But until we get into it, we don't know what's going to work, and not all ideas will actually work out. For myself, at least in my group, the future definitely, I think, is autonomy, space debris, mission support. We're trying to be involved in a few more deep space missions actually over the next few years. And that's been a big area. The other one that's coming up, I think it relates to a question you'll ask me a little bit later, is software. We're actually in my lab, we're developing some open source software, which is very unique to this field, that gives this common architecture and how to simulate space missions, do analysis, do your research, but also actually fly satellites with it. And so the software aspect, I think, are really growing. Yeah, just like on the Earth, when you look at what drones are doing and self-driving cars, software is just a key component. You got all the electrical systems and power efficiency and wheels and mechanical stuff and safety aspects, but the cars and these drones, they're really flying brains, flying computers. So I see a lot of that happening actually out of the lab as well, big software parts.
So what is something that you regret not doing throughout your career? Like from the beginning?
I really can't. I saw that question and I really don't have anything I can point to. I mean, I don't believe much in regret, because then it's always, you keep wondering, what if, and you can drive yourself absolutely bonkers doing that, because you don't know. It's like, oh, if I only taken a left, everything would have been fine. You have no idea. You took a left and then a micrometeorite takes you out, big deal. You just don't know. So I think it's important to go through life and make decisions. And you'll always come up to crossroads where all of a sudden you can go, well, I see 4 paths. And maybe they're 4 good paths. Congratulations. Maybe 2 of them not so good, 2 good. Well, then you have to figure out what are the good and not ones for you in your life at this point, But once you make a decision, you move forward. You stop looking backwards, because it's just going to drive you crazy. So anyway.
Yeah. So what do you predict is going to be the biggest innovation in your area of research in your lifetime?
Well, just in aerospace, engineering, I think it's this access to space. When I was your age and looking at this and want to become an engineer, you could learn to be an aerospace. As a comparison, mechanical engineering and aerospace, on the surface, very similar topics that we cover. There's subtle differences in the classes and other things. I mean, there are differences, but it's very similar on a high level, But as mechanical, I know I can graduate, I can go build that turbine, I can build this engine, I'm going to work on stuff and see how it works. As an aerospace engineer, you may work your entire life and never have anything actually fly. Access to space is so limited. So to get that one launch, you want to do, like, I know colleagues at Ball Aerospace. She was, I think it was Lisa Hathaway, gave a great talk to our department, and she was involved when they built the sensor for the probe that went past Pluto. She was like a young 20-year-old or something working on this, but it took forever to get there, and now she's a late career when finally it arrives. This is the aerospace career you might have if you work on these missions. This might be your whole life, just waiting for, does it actually work, now provide support and then finish it, which is cool. Yeah. What I really see as the next big discovery is just simply access to space. With SpaceX, Blue Origin's, bunch of companies looking at ways to get to space, to not just have these specialized astronauts, but others that can go to space, tourism. Tom Cruise now wants to shoot on the space station, go up the crew capsule to the next movie. I mean, how cool is that? I think that means for engineering too, things are going to really advance quickly. We want to build a lunar gateway station again. People talk about going, actually people going to Mars. That's going to require all kinds of technological advances. And if you're in a situation where you have to analyze everything for a decade, making sure every little math is right for the first, if you do something in engineering and it has to work the first time, your cost increases 100-fold.
Yeah.
If you can build something that gets you close and you go, okay, that's my first prototype. Let's build this plane, fly it. And you see, ooh, the wings didn't do what they're supposed to do. Great. Didn't land properly. You learned a lot. You fixed that. You try it again. Now it went much further. This is how SpaceX is flying now. They're trying to get this their Starship or whatever they call it. 14 landings didn't work. The 15th worked, and now they're going to try more. This is how we need to be able to get into space. And I think that's a fundamental shift from the last few decades, that we get to build, test, fail much more aggressively. And before, if you failed, your company was dead, because that just couldn't happen, and the money was left. Now, with the new models, there's enough money to do that, and therefore be much more aggressive. So I think you're going to see in your lifetime stuff moving in and out of space that's going to be much more common very quickly, thanks to that, and that'll change everything in this field. Yeah.
So to high schoolers like me and to younger generations, what would be your advice for us to be successful in this career?
Well, there's several parts. I mean, if you're a high schooler, right, you're trying to figure out what you want to do in life. And good grief, who really knows that for sure? What I hope you can figure out, I mean, some people have very clear paths. Good for them. I wasn't necessarily one of them. I was more like, I love this area of space, and I could have become an astrophysicist. I could have become a software engineer. I could have become a mathematician. I chose aerospace engineering because it combined a lot of things, but that was not my only choice. I could have been happy doing lots of things. I think this day and age, aerospace is a very interesting, because you can see it across the world. I give talks to different universities, the aero department, from Milan, from Delft, from the one in Singapore. It's one of the top ones in Asia. They have all doubled to tripled in size over the last 10 years. I mean, the growth has been astounding. And it's just permeating everything. So if you're looking for something that will have a lot of interesting, fun problems to work on, I think aerospace industry is something. You have to have a passion for it, because aerospace engineering is probably also one of the hardest engineering degrees you can get. Because where a mechanical and electrical, those are all very challenging degrees. But when you graduate as a bachelor's, you've already had a chance to specialize and get into this. With the aerospace, what makes it, I think, different is there's more breadth. You have to really understand also the mechanical side, the electrical side, yes, but also dynamics, orbits, materials, the control systems, the fluids, the air stuff, everything that we have to do there. And so you get a little bit of a lot of topics, which is why so many aerospace engineers actually continue to a master's degree, depending on what you want to do. So a lot of our students actually get masters. We have one of the largest master's program in the nation. To be successful in this career, so at your stage, really, I mean, it comes down to the STEM fundamentals: science, technology, engineering, and so forth. So to work in aerospace, math, physics, that's key. Engineering is basically applied physics. You learn the principles of how Newton's laws work. If you push against something, it pushes back, and how to deal with equations to predict motions and all of this stuff. But it's basically applied physics. So the language we speak is mathematics. You have to be good at math. And the tools we use are computers. And so you have to also be good with computers, and not just using computers. I think a skill set we're seeing more and more is how to write programs as well. If you have any opportunities to not just use computers, but actually learn a programming language, how to use Python. That's a very popular one these days, very modern language, or how to use C or something like that. I would say grab it, don't wait for somebody to impose this. Really look for opportunities to kind of bring the skills in. It's going to help you tremendously as you go through this program and get to apply that. The other thing is also, if you're not sure about fields, we have students visit. We give visits to high schoolers who come by. I've had high schoolers who kind of worked with some of my grad students for a semester. They come by 1-2 hours a week, help out with some basics. They can help with some plotting, understanding where things are going, just to get a sense of what it's like to work in these areas, And when you start, the thing to keep in mind too is as a high schooler leaving, going into college, you're not making the, wow, okay, I will be in aerospace, therefore I will only do aerospace for the rest of my career. We have students who start do the first year, and then some switch out of aerospace. They go into mechanical, they go into electrical, maybe they go into business. You know, it just depends. There's always opportunities. But anyway, my goal would say, what I would recommend is just see what you're passionate about and see what you're actually skilled at. I've had students come to me going, I am going to be an astronaut. I need to do this. You know, this is really my passion. This is my life. This is my vision. This is why it has to happen. But I hate math. I hate physics. I can't stand using computers, and I'm failing your class. I mean, that was literally what one student told me at Virginia Tech, you know, and I have to sit that person down and go, let's have a serious discussion about your career options, because what you described as not your skills, that's exactly what you need, you know. So just passion by itself doesn't mean, you know, but this person could also do other things, like in business. There's so many aspects to space now that you can be involved in the space business without being the mathy, you know, software person too. So, you know, go explore, go visit schools, go see if you can chat to some students. I think that would be great to help you kind of narrow down what looks good. Then make you, again, no regrets, make a good decision, what gives you the most opportunities. And then you will quickly learn what really resonates. We always find, I mean, it doesn't matter how old you are, at some point, everything sounds good and you start doing this position and you go, well, that sounded good, but doesn't quite resonate, you know? And then you find another thing that's maybe adjacent that you go, okay, that was nice, but now I'm discovering this other field I wasn't even aware of. And that really resonates with me. This happens all the time with my doctoral students. You know, we start out with some ideas and then all of a sudden they go, whoa, that looks even cooler, you know, and that's where I want to take my work. So that's just a normal part. You make your best guess forward. And I think aerospace is a fantastic way, but you must have, you know, stick to your math, physics, software.
Mhm.
That's a strong requirement for this.
All right.
Yep.
Well, thank you for giving me the opportunity to interview you. I think it was very productive in seeing, you know, a point of view of a professional and also a teacher and mentor to students. So yeah, thank you for the
Okay.
opportunity.
Well, Balomir, thanks for your time.
Mhm.
I enjoyed chatting with you.
Yep, me too.
Okay.
All right.
Great.